Hi, my name is Parmita Mehta. I am from University of Washington, and I will be talking about utilizing sampling for deep learning model diagnosis. Deep learning has been a valuable tool for gathering intelligence from high-dimensional data such as images, text, audio, and video. In recent years, deep learning models have surpassed human performance on vision benchmarks and on NLP benchmarks. One of the enduring criticisms of deep learning models is their opacity. What did the model actually learn? The black box nature of these deep learning models is a barrier to their adoption in applications such as medical diagnosis, where explaining the decision is essential. Regulations such as EU, GDPR formalize such requirements. Additionally, the black box nature of these models hinders debugging. Interpretable AI is an active field of research and it involves generating data artifacts to understand and debug deep learning models. There are several techniques for understanding deep learning models. These approaches consist of either looking inside the model to view the internal representation of the data, or looking at which part of the data is most responsible for the answer provided by the model. This can be done by taking partial derivatives of the target output with respect to the input data. We look at the methods that involve generating internal representations of the data. A study of the model diagnosis queries from literature shows that these queries look for one of three entities: the top K maximally activated neurons, average activation values, or the distribution of maximally activated neurons. These queries may be posed over specific layers or certain classes, and often compare these values over correctly and incorrectly classified items. The focus on maximal and top K values as opposed to minimal values is due to activation functions used in deep learning models. Thus, various techniques for model interpretation require generating, storing, and examining these artifacts to diagnose deep learning models. One way of doing this is to pre-generate the artifacts over the entire dataset. The size of this generated dataset varies as the product of the size of input data and the number of parameters of the deep learning model. This number is around 3 orders of magnitude larger than the input data size. The other approach would be to generate the data at the time of query. This results in queries taking tens of seconds to tens of minutes, which is far beyond interactive time frames. The ideal solution would be in the middle: interactive query times without having to generate all the data. Sampling is a natural solution for this problem. However, we find that uniform sampling or even stratified sampling by class or confusion matrix does not yield good results. Here, we utilize a key insight about how deep learning models work to generate a suitable sample. Deep learning models learn a lower dimensional representation of the data. Deep learning training transforms the input data, creating a new representation with each layer. Training criteria encourages the training set neighbors, such as data points from the same class, to have similar representations, resulting in lower dimensional representation of the input data. Leveraging this lower dimensional representation of learned by the model has a dual benefit of reducing the dimensionality of the data and focusing on the representation learned by the model. We pick the latent representation from the last hidden layer and utilize it to create a sample. We utilize the sample then to diagnose the model. Since now we are dealing with a much smaller fraction of the data, we can pre-generate the artifacts and achieve interactive query times. MNIST is a prototypical data set of handwritten digits, with each data item a 28 by 28 grayscale image. We train a convolutional neural network to classify this data set. For our experiments, the dimensionality of the latent representation from the last hidden layer is 84. Let's take a look at the latent representation projected into 2D space for the MNIST model. In this figure, each of the data items is colored by the class label. There are two things that are apparent from this representation. First, the items from each class cluster together neatly, and there's a clear separation between the class representations in the latent space. Secondly, the incorrect data items fall at the boundaries of each of these clusters. For machine learning models, the boundary between two classes, also known as the decision boundary, is where the model makes mistakes. We utilize this insight to propose a novel sampling technique for deep learning model diagnosis, where we use the distance from the boundary to determine which data items are included in the sample. We examine two ways in which items are included in the sample. For both of these techniques, we group the data based on the latent representation, and from each group, we select prototypes and outliers. For the first technique, unsupervised clustering-based sample, we utilize Gaussian mixture models. Gaussian mixture models are a probabilistic model for representing normally distributed subpopulation within an overall population. We use the distance from the center of each cluster here to select prototypes and outliers. For the second technique, max margin-based classifiers, such as support vector machines, we use the associated distance from the decision boundary for each data item and use this distance to determine prototypes versus outliers. Our samples consistently outperform other techniques on model diagnostic queries. Here we show the result for the top 10 neuron activation. We compute the top 10 neurons on our sample and then compare it with the top 10 neurons on the entire data set to determine precision, which is the y-axis. Higher precision is better. X-axis is the sample size, which we vary from 5% to 100%. Our methods of max margin classifier and the two clustering examples with GMM consistently outperform all three query types discussed previously. Deep learning model diagnosis requires additional artifacts. Generation, storage, and management of these additional artifacts create a significant data management burden. We present a novel sampling technique to alleviate the data management burden and significantly lower the time required for debugging and tuning the deep learning models. Thank you.